Hello everyone. Today we're going to do a lesson on work, energy, power, and momentum. Alright, so what exactly is work? So work is when a force acts across a displacement. So if an applied force moves an object across a displacement, the force is said to do work on the object. For example, if you push a book across the table, you're doing work on the book because you're having a force that acts on a displacement. So, however, you're not really doing work. So pretend you're pushing on a wall. All right? So you're not doing work. You can apply as much force as you want, but you're not actually doing work because the wall itself is not moving. So work is dependent on force, displacement, and it's also dependent on the angle between the force and the displacement. Why is that? Because only the component of the force parallel to the displacement actually does work. And that usually means the x component. So that means the component of the work perpendicular to the displacement does no work. So suppose you got a man walking with a suitcase. So the force supporting the suitcase is not doing any work on the actual object. Why? Because it's perpendicular, see? And if you plug this in the formula, 90 degrees, cosine of 90 will be 0. So the formula also works out. So here's a quick practice problem. A man is pulling a wagon with a force of 50 newtons, angled at 30 degrees at the horizontal. And he pulls the wagon a total distance of 30 meters. How much work is done on the wagon? All right. So this is basically a plug-in and solve type question. Right? Work is F times D times cosine theta, which is equal to 50 newtons times 30 meters times the cosine of 30 equals 1,299 joules. So that will be your work done on your wagon. So now we're going to move on to energy. Energy is one of the most important concepts in physics. So let's talk about energy. So energy is the ability of an object to do work. There are two types of energy, kinetic energy and potential energy. Kinetic energy is the energy of motion. A moving object has kinetic energy. Now, potential energy is stored energy, which can be converted into kinetic energy. The formula for kinetic energy is this. Kinetic energy, K, equals mv squared over 2, where K is the kinetic energy in joules. Notice it's the same unit as work, and this is not a coincidence. We'll see why in a bit later. M is mass in kilograms, V is velocity in meters per second. Okay? So you could see, like, kinetic energy is proportional to velocity. So you need velocity for kinetic energy, otherwise it's 0. And if you double your velocity, you will quadruple your kinetic energy. If you triple your velocity, you're increasing your kinetic energy by 9-fold. So you can see how dependent kinetic energy is on velocity. So gravitational potential energy. Why gravitational? There are other types of potential energy that we'll talk about later in physics and actually later this presentation. So gravitational potential energy is the energy based on height above the ground. So the higher you hold your object, the more potential energy your object will have. So you got your two skiers, right? Skier red and skier blue. Okay, they both weigh the same, 500 newtons, so their quantity mg will be both 500 newtons. However, the blue skier's at a higher height, okay? If it's at a higher height, it will have more potential energy, it has more stored energy ready for use. Which is why As you'll see later, the blue skier will ultimately be faster at the bottom. So this will be your formula for gravitational potential energy, which is equal to mass times g times h. We use the letter U for gravitational potential energy, measured in joules. M will be mass, g will be acceleration due to gravity on Earth, which is about 9.81 meters per second squared, and h will be your height. So let's start with a very simple practice problem. A 2,000 kilogram car is moving with a velocity of 25 meters per second. Find its kinetic energy. Again, this is plug in and solve. K equals 1/2 mv squared. Usually it will be written like that, but because of the computer, I just chose to write it like this, mv squared over 2. So you plug in your values, 2,000 kilograms times 25 meters per second, that's squared, and that divided by 2 will give us 6.25 times 10 to the 5 joules, or 625,000 joules. A lot of kinetic energy. So you might be thinking, hey, this unit's really easy, just plug in and solve, just equations. But this is where it starts to get hard, all right? So law of conservation of energy states that energy is always conserved unless external work is done. This means that unless there's external work done, all energy must be conserved and no energy can be added or removed unless there's external work. Okay, so you have a pendulum over here. Little pendulum swinging back and forth. So when it's swinging like this, it will stop momentarily at its highest point because it's its highest point. All the energy will be gravitational potential energy. Okay? So this will be its highest point. However, it will swing back down, and at lowest point, it will have its maximum kinetic energy. Right? Because it's the lowest point, and this is also its fastest point. Why? Maximum kinetic energy. All the potential energy will be kinetic energy. All right? Then it will swing back up and it will have its maximum potential energy again because it's at rest and it's at its highest point. So keep on swinging and an energy will convert from one type to another. Now you might be noticing, hey, it's off the ground, even at its lowest point. There must be some potential energy. There is, okay? But then there is or there isn't. You might be confused, but keep in mind that it's only the energy relative to like the place where you pick to be the 0 point. What I mean by 0 point is the 0 point is basically where gravitational potential energy is, quote, 0. And people use the ground as 0 point, the sea level is 0 point. However, you can choose it because the change in height will cancel. And you'll see what I mean in the later example. All right? And one more thing I should talk about is conservative and non-conservative forces, right? So some of the forces we know, like gravity, is a conservative force. These forces do work on an object if moved, of course, just a definition. But the total net work done on the object does not depend on position and does not depend on path traveled. So pretend you have a sphere, okay? Red sphere, energy 0, right? So you bring it up through the green path, very simple, okay? You bring it up, and that will be mgh, all right? That will be mgh. It will have this gravitational potential energy up here. Quite simple. However, if you do this crazy looking path right here, this blue path, well, it will still have the same gravitational potential energy. Why? Because it's the same change in position. It's the same height, all right? Sorry about that. It doesn't matter if you do this, and then you go here. You'll still have mgh potential energy. Why? Because gravity is conservative, right? The work it does is not dependent on the path it took. Non-conservative forces, on the other hand, do depend on the path the object takes, all right? So you have a book, okay? It's point A, this point B, right? You first push the book across the table, right? And then you bring it back, and then you push the book in like a semicircular type arc, okay? The work done will not be the same for both paths because friction is non-conservative. It will be greater there will be more work on the red path because the red path is longer, okay? So pretend you have this red sphere, right? You bring it up, and then you bring it down again, okay? So the work done will equal 0. Well, the net work, okay? Because energy will be 0. Pretend it's a 0 point. Energy will equal 0 at this point, right? Now suppose you did the same thing here. Okay? You move it all around the table. Total work will not be 0. In fact, it will be 4 times the work done from moving from one corner to the next. Because friction is non-conservative, and non-conservative forces do work based on how the length of the path it travels, the total distance it travels. Right, so let's finally do a practice problem, right? A 3 kilogram mass is tied on a light 2 meter long string. So if the mass is pulled back so that the angle the string makes to the vertical is 25 degrees, find the velocity of the mass at the bottom, right? So we're going to use conservation of energy, okay? Right? Energy initial must be energy final. And if we assume no air resistance, that means there's no net work done. That means energy initial must equal energy final. So that's mgh equals mv squared over 2. So here's where the 0 point comes in, all right? Say these words are the ground. Okay, you could use that as the 0 point, or what's even more convenient, you could use the very bottom of this arc as the 0 point, whereas it's minimum potential energy. That will be the, quote, 0 point of potential energy. That means only this change in height will be considered, and that's where we go here, all right? Length L, then we have length L over here, because we're assuming it travels in a circular arc, which pendulums usually do. So it will swing down, and if you use a little trigonometry, I did give you the angle, 25 degrees. You could notice that this side is L cosine theta. You could just use the cosine ratio, right? So this length, this little change in height here will be L minus L cosine theta. L minus L cosine theta, right? That means you just substitute in. First you cancel out the masses because mass is canceled. Then you substitute in for H, L minus L cosine theta. So that's how much height change you've gotten. That equals V squared over 2. If you multiply by 2 and I choose to factor out L, take the square root, right? You get square root 2GL 1 minus cosine theta. Then you square root, you sub in the numbers, 2 times 9.81 meters per second squared times 2 meters times the quantity 1 minus cosine 25. That gives you about 1.92 meters per second. So this is how you do this type of problem. So here's where the 0 point thing comes in. I'm going to do this problem without using the 0 point method, and then you'll see why the 0 point method could be a lot easier. So a block slides down a 10-meter frictionless hill. It launches up at an angle of 45 degrees at a point 4 meters above the bottom of the hill. So pretend this is the bottom, right? So above the ground, I should have said. Find the distance x from the launch point the block travels before landing. Okay, so you can see some kinematics will take place here. But first, let's do our conservation of energy. So we have our initial potential energy over here at H1, okay? Will be turned into mv squared over 2 plus mgh2, all right? So that means if you cancel out the m's, you have v squared over 2 equals gh1 minus gh2, right? You take the square root, and then you can factor out g, and you get square root 2g h1 minus h2. Now, we're going to analyze this expression a little bit. What is h1 minus h2? That is just the total change in height, right? Which is why the choosing a 0 point works, because it's just a change in height. I use this as the 0 point, and this expression brings us the change in height. The higher height minus the lower height, we equal the height from this to that. Okay? So this problem also could have been done if the level ground was the 0 point, because this is the change in height over here. So if you substitute everything in, you had square root 2 times 9.81 times 10 minus 4. That equals about 10.85 meters per second, right? Now here's where some kinematics gets in, if you remember your kinematics. So VFY, I'm going to use this equation, why? Because it's convenient. VFY equals V naught Y plus AT, right? That means we're solving for the time it takes to get to its maximum point, right? Because assuming air resistance is negligible, this path is symmetric, so the time it takes to get here will also equal the time it takes to go down. So we'll call this time T naught. If you solve for everything, remember at the very top V naught Y will be 0. At the very top VFY will be 0. 0 meters per second minus 10.85 meters per second times sine 45. If you don't know what this expression is, that means 10.85 times sine 45. That's just how you find a y component. Use the sine ratio. Look at my video for kinematics for more about that. Divide by negative 9.81. Acceleration's downward. Meter per second squared, which is equal to 0.782 seconds, right? So the actual time, TF, will be twice that, assuming this symmetry over here. We go 1.564 seconds, and then you could substitute in the x equation, x equals vxt. You could always derive this by using the general definition of velocity, because as you can see, just that general definition of velocity solved for x. That equals vxt, which equals 10.85 meters per second, then cosine of 45. Again, these two is just how you find the x component of the velocity. Due to space, I didn't want to find it separately, so I just stuck them in the expression. 10.85 times cosine 45 times 1.564 seconds, which equals very, very, very close to 12 meters, right? So almost exactly 12 meters from the launch point this box will land. So if a block of mass 2 kilograms slides down a ramp 8 meters tall with an initial speed of 2 meters per second, all right? So what should you make the coefficient of kinetic friction between the floor and the block? So what should the coefficient of kinetic friction be if the block stops 2 meters from the base of the ramp? All right, so this is different because we have some work involved, some external work. So the work will be done by friction, and we're trying to find out the distance at which this friction does work. All right. So we have mv squared over 2 plus mgh. There's mv squared over 2 because the block has some initial velocity. Coming from 8 meters, so there'll be some mgh as well. Plus some work by friction should bring the block to 0 by 2 meters, okay? So that'll be, and we're trying to solve for the mu k needed. So we're going to do mv squared plus mgh equals this crazy expression, negative mu k mgx cosine theta. Cosine theta is from the formula. X is the distance, so that's from the formula. Mu k mg, right? So that's just a expression because mg for a fn from the formula. On a horizontal surface, they'll be balanced out by mg, right? Because it's not moving up or down while it's just sliding across horizontally. So Fn should balance out mg. So Fn will be, normal force will be mg. So that's where this mg expression comes from. You cancel out the masses. We get v squared over 2 plus gh equals negative mu k gx cosine theta. Right? Now what I'm going to do, excuse me. What I'm going to do is, I don't like fractions. Dealing with fractions, it will, especially on a computer when I'm typing these up. So what I would do, I don't know if you would do this, but what I did, I just multiplied both sides by 2 to get rid of this fraction. So we got v squared plus 2gh equals negative 2 mu k gx cosine theta. And if you, okay, so we solve for mu k equals v squared plus 2gx divided by negative 2gx cosine theta. And if we substitute these numbers in, you might realize negative, why negative? Mu k cannot be negative. Well, in the real world, mu k cannot be negative. Then cosine of 180, that means cosine 180 will be negative 1, all right? So negatives cancel out. We get a mu k of 4.101 about. That's from this math. And yeah. There's no material with a mu k that large. In fact, there are not even like many materials with a mu k of just above 1. So the mu k this large shouldn't practically exist. So this problem's kind of wrong. But yeah, so you won't get this block to stop in 2 meters. Because this mu k is just way too large. But at least it showed you how to solve these type of problems where you have conservation of energy with external work. So now I'm going to talk about a bit about springs and put springs, well, hopefully put springs into our definition of conservation of energy. So this is just an introduction to Hooke's law. So springs are very useful devices that exist in many modern pieces of technology. And what's quite remarkable about these springs was discovered by a physicist, Robert Hooke, who came up with Hooke's law. And that law states that the force the spring exerts on an object is directly proportional to the distance the spring has been compressed or stretched. So in equation form, Hooke's law is this. The absolute value of Fs equals kx. Why absolute value? Well, some books and some sources will write this equation as Fs equals negative kx, because if you give it a downward displacement, the spring will want to pull up. But if you compress the spring upward, you compress the spring upward, then the spring force will be directed downward. So this proportionality constant, this is constant k. This k is what is known as the spring constant with units of newtons per meter. This spring constant is defined by the different properties of the spring, what the spring's made out of, how stiff is the spring, how elastic is the spring, how many coils, all that stuff. So that's how the spring constant is figured out. So you get to use this equation. We'll study it more in a later lesson, this equation more. But what we really want to know for this unit is elastic potential energy. This is a type of potential energy from which the name suggests comes from the stretching or compressing of elastic materials, and we're just going to use springs. However, this formula does not apply for just springs. It applies for anything elastic, like a rubber band, for example, or a slingshot, as long as they have a measurable spring constant or like force constant. That's also what this is known. As long as it has this, you could use this formula for anything elastic, okay? So this formula is U for potential energy, E for elastic, equals kx squared over 2, or 1/2 kx squared. All right, so where k is the spring constant in newtons per meter, x is the distance from equilibrium in meters, and U is the potential energy, elastic potential energy in joules. So we're going to talk about the relationship between work and energy. Previously, I said that both work and energy was expressed in joules, and this is not a coincidence. Work and energy are very closely related. Work is just defined as the change in energy. Work is just a transfer of energy in a system. So if you do this is the work energy theorem, or the work energy principle. It states that the total work done on an object is the change in its total energy. Right? So if all energy is conserved, then there'll be zero change in energy. That means there'll be no external work. And this fits in with conservation energy. This can just be figured out from conservation energy, that external work will add or remove energy from a system. So here's how you solve conservation of energy problem solving. So number one, so you should make a list of all the energy types in the initial state and in the final state. Then set those energies equal to each other. If for conservation of energy, add work on the left side if you have some external work being done. Then solve for the variable you're trying to find. This will reduce the chance of silly mistakes. Because if you just put numbers in it initially, you'll get confused with all the numbers floating around. So what I would do is just solve for the variable symbolically, as in variables. And then I'll just plug in and solve right there. Then I have all my numbers in one spot and my thing I'm trying to find in the other side. So here's our first problem. A block of mass M equals 10 kilograms is sliding down a frictionless 30-degree incline 2 meters tall toward a spring with constant K equals 1,000 newtons per meter. The spring's natural length is 1.5 meters. How far does the spring compress? And how much work does the spring do on the block to make it stop? Right, what I'm going to do is I'm going to take draw mode on. Right? Because this will require some thinking. Right? So that we said this is 2 meters tall, right? And this is 30 meters tall. So you could either use trigonometry to find the total length, the hypotenuse, the length of the inclined plane, or you could just use 30, 60, 90 triangle relationships, and you can find out that this hypotenuse will be equal to 4. So this will be equal to 4. And you'll see why I'm even doing this, like right in the next step. But now, since the spring has a natural length, we need to account for its length as well, right? So if this is 1.5, as we said before, 1.5 meters, I'm not even using units, just makes it look cleaner. It's 1.5 meters, okay? Then this length will be 2.5 meters. This length will be 2.5 meters. Right? So that means, I'm going to highlight this in red, this length will be 2.5. 2.5. All right? So if you actually want to do this, then notice this is parallel to this. These two are parallel. That means these two are corresponding angles. So this is also 30 degrees. 30. Then again, you can use some trigonometry to find out that this height, I'm going to highlight this in red. This height will be equal to 1.25 meters, okay? So that's where we get this, 1.25 meters. That's the actual height, right? We're going to neglect any further change in height because that's where potential energy, elastic potential energy starts to take in. So you have UG equals UE, you have MGH equals kx squared over 2, right? So that's x equals square root 2 MGH over k. Then if you don't know what we did, we just set these two equal to each other, multiply both sides by 2, divide by k. Remember, for simplicity, we're just going to neglect any further changes in height. It will still go down a little due to compression of the spring, but we're going to neglect that. It will not be that much to be concerned about because, elastic potential energy will start to absorb all the gravitational potential energy. So if you look at this, 2 MGH over K, we're going to substitute everything in, get about 0.495 meters, right? So if you want to find the work, it's not easy finding the work when this force varies with the compression, and so we could just invoke the work energy theorem. So work equals a change in energy, so that would be EF minus E naught, where E naught is the initial energy, EF is the final energy. Final energy is 0, right? Because we're going to choose this point as the 0 line. So final energy will not be moving there. We're neglecting any changes in potential energy after that. So 0 minus MGH equals 0 minus 10 times 9.81 times 1.25. Will be about negative 122.63 joules. All right, I'm going to just turn draw mode off. All right, let's move on. So here's a harder practice problem, okay? So a 100-kilogram man is performing a stunt in which some machine compresses him back to a spring with constant K equals 80,000 newtons per meter. I said machine, it's a huge spring constant, a distance of 0.2 meters. The beginning track is frictionless, but the incline part, this part, has friction with mu k equals 0.5. So part A, what is the man's maximum speed? And part B, how far the incline does the man go? All right, so as you can see, very messy, but it's a good problem. So part A is easy, just conservation of energy. So you have elastic potential energy plus some gravitational potential energy. They already marked out a 0 point for us. That's its dotted line, right? UE plus UG equals K, right? So that's kx squared over 2, or 1/2 kx squared plus MGH equals 1/2 MB squared. And since they're two fractions, it's even better to just multiply by 2 and get whole number coefficients. So if kx squared plus 2 MGH equals MV squared, and if you divide by m and take the square root, you get square root kx squared plus 2 MGH over m, which equals square root 80,000 newtons per meter times 0.2 meters squared, plus the quantity 2 times 100 times 9.81 meters per second squared times 10 meters. All that over the mass of the man, 100 kilograms, will be equal to 15.11 meters per second. See, that was not hard, right? Now, the hard part comes here, okay? So kinetic energy plus the work, all right? You're adding work. So there will be some work will equal the UG. I should put a G over here. It's gravitational, okay? It's gravitational, so it should be UG. So that'll be mv squared plus mu k mg d cosine theta equals mg d sine theta. All right. So I'll take off my drawer back up again. Oh, sorry about this. Let me just turn it off. All right, so you have d sine theta. Where did that come from? Most of you might ask. Now, if you see, okay, you will enter this ramp with this velocity. Then we'll stop maybe here. It's just an approximation, right? This distance, I'll just call it d because that's what I called it. So that's d, right? This is h. This is the mgh in the gravitational potential energy. And this is our little theta. This is our theta. This will be our theta and or 30, which equals theta. So if you use a little trigonometry, you'll see that sine of theta equals opposite over hypotenuse, h over d, and you'll see that h, if you multiply both sides by d, we can see that h equals d sine theta. D sine of theta, d sine theta. So that's where this is basically h. This is basically h. So mg d sine theta, we have mv squared over 2. I'm going to subtract this work expression, mg d sine theta minus mu k mg d cosine theta. All right. I could have just canceled them out canceled the m's out, but who cares? So mv squared over 2 equals d times mg sine theta minus mu k mg cosine theta. All right. Then we have mv squared over the quantity 2 times mg sine theta minus mu k mg cosine theta. All right. 2 times. So that's d over here. So we just divided both sides by this expression. So that will be d, right? Thought I almost made a mistake. So if we substitute all of these, I won't even try to say all of these, just a lot of numbers. We get 15.5 meters. And that's a huge, even with this huge coefficient of, coefficient of kinetic friction, he will still slide up 15.5 meters. And just to give you a sense of context, this maximum velocity, 15.11 meters per second, right? That, if you punch in your calculator and convert to kilometers per hour, that would be 54 kilometers per hour. So that's the size, that's like a speed of a car on like a local road. Like a car speed. So that's how fast he's going. He has a ton of energy, so even friction, he'll still slide up 15.5 meters. Turn draw mode off. Let's move on with power. So power is the rate at which work is done over time. So basically, if velocity is the rate of change in position over time, so displacement over time, power is basically work per time. Right? So in that sense, that's power. Power is measured in units of joules per second, or they have a special unit, the watt. So you're measured in units called watts. So you'll usually see light bulbs rated in watts, some generators rated in watts. So some like microwaves rated in watts. So that's basically their power output. So you can see the formula for power, P equals work over time, W over T, very simple. So here's our first practice problem. A workman can lift a 20 kilogram box to a height of 5 meters in 2 seconds. How much power does the workman use? Oh, sorry. How much power does the workman use? So you just use the work energy theorem. So final energy is mgh, initial is 0, so it'll just be mgh. You can substitute this right in for work over here for symbolic expression, mgh over t. And if you put in the numbers, 20 times 9.81 times 5 divided by 2, that equals 490.5 watts. So that's the power the workman will exert. So you can manipulate expressions, the equations, to find another useful way for finding power. All right? So as you can see here, power is work per time. So we get into definitional work. We're just going to ignore the cosine theta part for now. Although there will still be a cosine theta. The final expression is just a simple version. So FD over T, right? And then you could like separate out the D over T, because so F times D over T, and D over T, that's basically velocity or speed. So that's basically velocity. So another way of finding the average power. You see why I put average? Because this is not the exact, just the average power. It's not the instantaneous power, because you're not finding the instantaneous velocity or the instantaneous force. So it's just the average power. P equals FV. So it's another useful way of finding power. So let's say block M1 is nailed to the table and has a 50-watt motor inside it that can wind up your string. So connected to that string is a block M2 with mass 10 kilograms. Okay? So, and it's tied to a pulley. If the motor is turned on, how fast will the block M2 go? Right? So net force equals 0. So the force bringing it up is T minus mg, which is 0. So the total force will just equal the tension, so the force pulling it up will be tension, which will be, the magnitude of it will be equal to the gravitational force mg. So P, if you can use our simplified definition, assume constant velocity, P equals FV equals mgv. So we just substitute an mg for F, mgv. And if you solve for mg by dividing both sides by mg, we have V equals P over mg. All right? So we have 50 watts divided by 10 kilograms times 9.81 meters per second squared, which is about 0.51 meters per second. So that's how fast your block will go up. So momentum. So it's probably our last topic. So momentum, so here's an introduction to momentum. Momentum is a property of an object in motion, which is the product of the object's mass times its velocity. So it can be used to measure an object's inertia or a natural tendency to change its motion. So an object with a large momentum will be hard to stop. It will also be hard to get moving. However, an object with a low momentum will be easy to stop. And again, it will be easier to get moving. We use the letter P to symbolize momentum, and as its own little derived unit, kilogram meters per second. So this is your formula for momentum. P equals mv, just from the definition. Where P is a momentum in kilogram meters per second, m equals the mass in kilograms, and v equals the velocity. All right? I think why we're learning this is just a formula, just some random property. Right? But we'll learn later that this property is actually quite cool. But first, let's talk about impulse. So the impulse is defined as a change in an object's momentum. All right? This equation can be written as this huge expression. J, we use J for impulse. You can use J impulse, which can be either measured in kilogram meters per second, basically momentum units, or Newton seconds, which is from this quantity right here. So J equals change in momentum, which is equal to mass times the change in velocity, which is equal to force times the change in time. All right? So let's just do a practice problem. So a baseball pitcher throws a 0.52 kilogram ball at a speed of 38 meters per second toward the batter. So the batter hits the ball at a speed of 45 meters per second toward the pitcher, which, yeah, right toward the pitcher. Same, like, plane. All right, so the bat is in contact with the ball for 0.5 milliseconds. So that's what that M means, milli. So 1,000th of a second, milliseconds. Find the magnitude and direction of the force the bat exerts on the ball. Right? So you can use one of our formulas right here, m delta v, which is mass times change in velocity. You can also substitute f delta t for j as well, this last formula. So f delta t equals m delta v. You just divide by delta t to find f, and you get m delta v over delta t. And here's where people get like stooped up. They'll say, hey, 0.52 kilograms, so 45 minus 38, that is not right, right? Because it changes direction. So say toward the batter will be left. So he's throwing left, and then the batter hits the ball at a speed of 45 meters per second toward the pitcher. All right? So the velocities will change direction. So you have to account for that change in direction, 45 minus negative 38. Divided by 0.0005 seconds, which is 86,320 newtons, which is a law of force, right? So one thing I may have forgotten to mention is momentum, like force and velocity and displacement and acceleration. Momentum is a vector. So momentum's a vector quantity, so it's unlike work or energy, it has a direction. So why we have to account for direction over here. So the overall change in momentum, you would have to use some signs there, as in like negative, positive. Another interesting to know is, let me just turn on draw mode for a second. Right? What happens if we draw parentheses here? Right, just for the symbolic expression, that'll be m times the quantity delta v over delta t, right? And what is equal to delta v over delta t? That's acceleration. That's acceleration. So that is also the part where y impulses f delta t. I'll do a full scale, like maybe derivation in a later video, but this is quite cool. So if you isolate that equals your second law expression. So just something cool to note about, to take a note of. So this is that cool property I was telling you about. So momentum has this cool feature where it's always conserved. So like energy, momentum cannot be created or destroyed, but transferred. So in other words, the total momentum of a system cannot change unless an external impulse is applied. So if you got this impulse applied, you got this force applied, that means momentum can change. You can add momentum or take away momentum because you'll transfer momentum through that impulse. So mathematically speaking, the total momentum, that's the sigma again, the total initial momentum must equal the total final momentum, unless we have impulse. So next we're going to talk about inelastic and elastic collisions. Right? So there are two types of collisions, inelastic and elastic. Right? A perfectly elastic collision means that all energy is conserved during the collision. So conservation of energy works. So right here, this white ball, the striker ball, if you're talking about a pool table. Sorry, excuse me. So they will go with the velocity v1. Then momentum is conserved, but this stops. This will go at the same velocity v1. This is an example of an elastic collision. So they just collide without any friction or sound energy or heat energy. Just all energy is conserved. All right. Inelastic collision. A perfectly inelastic collision means that energy is not conserved. Right? The objects will stick together and or join as one object. All right? So here's an example of an inelastic collision. So M1 traveling to the right with V1, M2 traveling to the left with V2. They will stick, so they'll join this combined mass M1 plus M2 with some velocity V, all right? So through this, then there will be some energy loss as sound and heat, especially as the two stick together, and it loses some of its like elasticness. So these are inelastic. That means energy is not conserved, and perfectly inelastic means they just stick together. So once they touch, they just stick. So most everyday collisions are just half elastic, half inelastic. So like that 50% of both, so a mixture. So we're gonna do like 2 practice problems. So this is an easy one. The next one's gonna be a harder one. So 2 hockey pucks, one of mass M1 equals 0.2 kilograms and the other one mass M2 equals 0.08 kilograms, travel at 4 meters per second and 3 meters per second respectively. If the large puck hits the small one and moves at a velocity of 1.5 meters per second after the collision, how fast is M2 moving? So what you can do right here is you can just sum up your momentums. So you have some initial momentum over here, initial momentum over here, and you'll have some, for M1, you'll have some initial momentum of M2. So they both add up and they must equal the momentum after the collision for M1 and the momentum after the collision for M2. All right? So you could subtract M1 V1F. So V1I is your initial, V1F is your final. So you can subtract this, and then you could divide by M2. All right, so subtract M1 V1F, and then divide by M2, and that should give you an expression for V2F. So that equals M1 V1I plus M2 V2I minus M1 V1F, divide by M2, and if you add it, if you put in all these numbers, you get 3.7 meters per second. So that's how fast M2 will go. So as you can see here, this is a harder one. So much harder one because this problem is symbolic. Symbolic meaning no numbers, just in terms of the variables given. So this is more like an AP type question. So a bullet with mass M is fired with an initial speed into a wooden block with mass M attached to a string with length L. The combined bullet and block system swings to an angle of theta. Express all answers in terms of M, little m, big M, L, theta, and a physical constant if appropriate. So part A, find the maximum height to which the bullet and block will swing up to. All right? So if you want to do that, all right, we just invoke the same strategy of what happened. So in the last one, so it will swing up to here. This will be your change in height. So if this is your 0 in height, this is your change in height. And assuming this little string does not stretch, this will be L, and this will also be L. Right? You can use a little trigonometry to find that this length is L cosine theta. That means this length, this little change in height here will be L minus L cosine theta, which they factored out will be L times the quantity 1 minus cosine theta. So here's the hard part. So the hard part is actually finding the initial velocity. All right? So what this initial velocity is, so what you can do here is you could just use n plus m v squared over 2. So that's kinetic energy will be your potential energy. Then the m plus m's will cancel out. This is gone. This is gone. We're left with v squared over 2. I don't know why this 2 is here. It shouldn't be here. So forget that 2. I think it's a typo on my part. So n plus m gl times 1 minus cosine theta. And that should give you the same speed as last time, square root 2 gl times the quantity 1 minus cosine theta. All right? So now we can just use conservation of momentum. So mv naught, so v naught will be your initial velocity. So mv naught equals m plus m, so our combined mass, times square root 2gl times 1 minus cosine theta. So that's our velocity here. So m plus m, that's our velocity. So it's just conservation of momentum. And you get v naught as this complicated expression over here. So quantity m plus n times the quantity square root of the quantity 2 times g times l times the quantity 1 minus cosine theta, right? All of that just divided by m. So that'll be your v naught, right? So I'm guessing that this is it, okay? It was a long presentation, a lot of concepts. However, it's just 2 conservation laws, setting the initial and final states to each other, keeping track of whether there's work involved, and adding work to the left side to account for the work done, or in the case of momentum, adding the impulse, finding impulse, and also keeping in mind that momentum is a vector quantity, so it has direction. All right? So this is it for our lesson. If you have any questions, please let me know. And please comment on this video with any questions. I'll try to help you as much as I can. Thanks for watching.